Okay, so let's look at a specific model for the interseasonal oscillations, especially for specifically designed for MJOs. When you write such process models, you make lots of assumptions. In this case, we are assuming that MJOs are a perturbation, let's say, on the seasonal cycle, and there is an interaction between MJOs and the synoptic scale systems. So you start with the momentum equations for the zonal and meridional direction. You have the acceleration terms, you have the Coriolis term, you have the pressure gradient term, you have the forcing terms, or you can think of them as also frictional terms depending on where you are. And these are the nonlinear advection terms between the seasonal and perturbations and seasonal in terms of gradients and means. And then these f to the superscript u is the nonlinear interaction term between MJOs and the synoptic scale. So you can have upscale cascades or dissipation in the downscale direction. So these are the mu and mv terms here, which as you can see, u bar du dx is the perturbation momentum advection by the mean flow, background flow, and the let me do the laser pointer again. I always lose the okay, so the perturbation velocity advecting the mean background flow gradient and so on, and same thing for the vertical and so on. So you can once you write this way, you can assume that the background state is non-stationary, and you end up with simplifications and linearization of the equations, often leading to analytical solutions and so on and so forth. I'm not going to go into gory details that go into these models, because this is one specific model and there are other models, so we will just use this for explaining the various multi-scale processes that we looked at in the schematic in the previous podcast. So there is a mass conservation equation for the perturbation flow. Omega is the velocity in the pressure coordinate, so it's the w vertical velocity in the z coordinate that's projected onto the pressure coordinates, which is the natural coordinate for the atmosphere. And this is the thermodynamic energy equation. So you have the stability parameter and the vertical velocities in pressure coordinate. You have the heating term here, and you have again the nonlinear interaction between MJOs and synoptic scales, and this is the Newtonian cooling term, which you can think of as OLR, balancing the energy at the top of the atmosphere. Actually, it's a gradient in the pressure, but you know the OLR has a profile as well. So it's a simplifying assumption which is not always very robust, but there you are. And then you have the M term here defined this way for the gradient of geopotential in the pressure direction and the x and y directions. This is the water vapor balance that we will see in the next page. Water balance, so you're integrating from the surface to the upper layer with a negative sign, and you have the various terms where you have to balance the moisture, divergence term, evaporation term, precipitation term, and this advection term that we talk about here. Okay, so those are the kind of basic questions, and then this is for the free atmosphere, and then you can tack on a boundary layer where you make the assumption that it's uniform in the vertical, so you make it a barotropic layer, which then becomes a half a layer in the jargon of how mathematically this is represented. So the humidity between any two pressure levels P1 and P2 is given by the air specific humidity humidity at the surface, which closely tracks the sea surface temperature and the pressure differences. The M here is the scale height ratio. So H is the density scale height to the water vapor scale height H1. I think if you don't know what the scale height concept is, you can look it up. It basically is the height at which any given quantity falls off by 1 exponential. Okay. So over the ocean and on time scales of a month or so, Q0 is well correlated with SST and may be approximated by the following empirical formula. So Q0 here is a function of SST, and it's been linearized in this way. Obviously, this is the relation between Q and SST is nonlinear, but when you take over time, you can write a linearized form this way, and then the latent heat release due to precipitation or condensation is related to, is constrained essentially by water vapor or humidity, has to be, right? So that gives you ways to estimate various things. And the boundary layer dynamics is done this way. So you have the wind stress terms here in addition to the pressure gradients for the momentum equation term, and you have the mass conservation equation again given this way. If you don't understand these equations, then don't worry, but basically when you do the atmospheric equations in the x, y, and pressure coordinate, you can get rid of density, which is a very inconvenient variable. So that's how you end up getting this form of the mass conservation equation. Looks like a non-divergence equation of an incompressible fluid, whereas the atmosphere is a highly compressible fluid, and that's the convenience of doing things in the pressure coordinate. Such a model obviously also requires a large number of assumptions about the bottom boundary condition, top boundary condition, typically rigid lid in this case, and then you have to have boundary conditions for what happens to tau xp and tau yp at the surface and at the boundary layer, top of the boundary layer, where you have to match the free troposphere, free atmosphere, and you need all kinds of assumptions. So here PE, pressure at the top of the boundary layer, is assumed to be 900 hectopascal. Half pressure depth of the free troposphere. Sea surface temperature is prescribed. Dry gravity wave speed of the baroclinic mode. Horizontal momentum diffusion coefficient, precipitation efficiency coefficient, which is something that simplifies the thermodynamic calculations, along with the convective parameterization, vertical turbulent viscosity in the boundary layer, depth of the atmospheric surface layer, surface roughness depth, where you match the wind stresses to the bottom boundary condition, heat exchange coefficient, heating coefficient due to wave convergence, heating coefficient due to friction convergence, heating coefficient due to evaporation, Ekman number at the boundary layer, non-dimensional boundary layer depth, half depth of the free troposphere, and some of these coefficients have an impact on the solution. For example, the Ekman layer in the boundary, Ekman number in the boundary layer, and some of the diffusion coefficient, these things have consequences, and people debate about it. But once you have these equations and the model, you can assume a single layer in the free troposphere and the boundary layer, so it's a 1.5 layer model in that case. So you can consider the linear frictionless adiabatic motion of the dry atmosphere in a quiescent environment, so the background flow is stationary. So the frictional terms, mean flow terms, all the heating terms and moisture equations get neglected in the set of equations we looked at here, 10.1, and the solutions then the static stability parameter SP is a function of pressure only. So you are here looking at the normalized amplitude in the non-dimensional pressure coordinate of the vertical structure of the vertical pressure velocity for the first 4 modes computed for an isothermal atmosphere, in which the static stability parameter is proportional to the inverse of the pressure square, no water vapor. Vertical pressure velocity vanishes at the upper and lower boundaries for all the modes, and the gravest baroclinic mode here has maximum velocity in the middle here, and you have the other modes having multiple zero crossings in the atmosphere. So note that the boundary layer here is below, so we are showing from 0.9 to 0.1 in the pressure coordinate. So this kind of calculation can be used to basically argue that to do the MJOs properly you need at least 2 layers. So here we are showing it more explicitly, and for the further discussion we will do with the 2.5 layer model for the intraseasonal oscillation. So you have the boundary layer at 1000 millibar is the surface, 900 millibar is the top of the boundary layer. You have boundary layer velocities UB and VB, humidity Q bar B, which is very critical because this is what drives the moisture mode or the moisture dynamics that creates instabilities and drives convection and so on and so forth. So you have 2 layers here, WE at the bottom with phi, W2 in the middle here at the interface of layer 1 and 2 at 500 millibar, and then middle of that layer is at 300, middle of this layer is at 700, and you carry the average quantities U1, V1, Phi1, U3, V3, Phi3 here. Of course, at the interface you have the index 2 being used. Okay, so I didn't go into large number of details that go into building such a model because it's a specific model, and going through all the details is a lot of work, and it's not going to really be needed for our purposes here, where we are just trying to get introduced to the processes involved in the intraseasonal oscillation. So I will highlight just the main points as we go forward, but if you are comfortable with these sorts of models and these sorts of equations, then you can read the chapter and the related papers. This model is being used by Bin Wang's group for process understanding. As I said before, the full GCMs are often used to predict MJOs, understand MJOs, and so on, but these process models, simplified process models, help a lot to interpret the results and to also see what may be missing in the full models, or what may be the biases, or how the biases may be affecting the MJOs, and so on and so forth. Okay.